In this video, we are going to be talking about the independence of two random variables, x and y, and we are going to base ourselves on, or take as inspiration, the single variable case, the independence of two events. So if we think back to early probability, then the events A and B are independent if and only if the probability of A intersect B is the probability of A times the probability of B. That is one possible definition. The other definition, right, they are equivalent, uses conditional probability, and that would be the probability of A intersect B is equal to, well, this is the multiplication rule, the probability of A given B times the probability of B. And the equivalent definition of independence is that the probability of A given B is just equal to the probability of A. And so those conditions are equivalent, and so the two definitions, either this one or this one, can be used for independence of events, and we are going to base ourselves on this version of it. And so we're going to see a direct mirroring of that law here in the discrete and in the continuous case. You have to remember this little PMF here, this joint PMF, is the probability that x is equal to x, and the comma meant and y is equal to here. So if that is and, we are using exactly this rule up here, and we are saying that we are multiplying the probability that x equals x, that is the marginal PMF of x, and the probability that y is equal to y. This is the probability x equals x times the probability that y equals y, the marginal distributions, the marginal PMFs. And very, very similar thing in the continuous case, the joint density function, if x and y are independent, will be the marginal density of x times the marginal density of y. And if these things are not satisfied, if they're not satisfied for all x and y, then x and y, the random variables, are not independent. They are said to be dependent. So let's go back and look at the examples from the previous video and see whether x and y were independent or not. So let's go ahead and look at example 1, where we had this table here, which gave us the joint PMF, so the probability that x is equal to x and y is equal to y, so little p of xy, and we had the two marginal distributions. And so the definition says for every single pair x and y, we need to have this product up here be true. So let us check if that is true. In fact, if we check for the very, very first one, the p of 1, 1, right, the p of 1, 1, that is right here, is that equal to the probability that x is equal to 1 times the probability that y is equal to 1? Is that what happens? So p of 1, 1 is 0.12. That is not equal to 0.2 times 0.5. Those are these values here. 0.2 times 0.5, that's this times this. In other words, the two marginals, they are not equal. 0.12 is not equal to 0.1. And so x and y are dependent. They are not independent. The next distribution that we looked at was a joint density. The joint, number 2, was the joint density of x and y was this. F of xy was 2x plus 4y on this region, which was the triangular region in the first quadrant with intercepts of 1 and 1. And the marginal function that we calculated was for x, 2 minus 2x. The marginal function for y was this one, y plus 1 plus 2y minus 3y squared. And we are looking to see the rule from up here. Is the marginal of x times the marginal of y equal to the density, to the joint density function? Well, it should be pretty easy to see that it is in fact not. If you multiply the marginal of x times the marginal of y, right, here they are, you multiply them together, you expand, and you will see quite clearly that this is not equal to this for many, certainly not for all values of x and y. So it is not the marginal, the product of the marginals does not give the joint density. And so x and y were again dependent in that previous case. So both cases that we looked at were dependent. What does it look like if x and y are independent? So let's look at a couple more examples here. First example, the joint density function for x and y is given as f of xy is 1/9 x times y on this interval, which is a rectangle. The rectangle from x is 0 to 2 and y is 0 to 3, so our support is this rectangular region here, and 0 outside that rectangle. So show that x and y are dependent. So if we want to show, we need to calculate the two marginals, take their product, and show that it is equal to the density, the original density. So if we calculate the marginal for x, then we are integrating out the y. So we are integrating over the range for y, so from 0 to 3, right? The definition had us go from minus infinity to infinity, but we've got a whole lot of zeros there, so we only need to integrate over the non-zero support for y. And so we're integrating out the y, we're integrating with the y, so our answer is not going to have a y in it. So here the 1/9 x is a constant, we anti-differentiate the y, plug in the bounds, top minus bottom, and we get the marginal for x is 1/2 x. Now if we do the same thing, for y, so we want to integrate out the x. We want to get rid of x, and we're going to integrate over the entire range that x is defined on here, where it is got non-negative density. So from 0 to 2, again, simple antiderivative, top minus bottom, simplify, and you get 2/9 y. That is the marginal density function of y. If we multiply these two things together then, so if we multiply the marginal for x with the marginal for y, so f sub x, f sub x of x times f sub y of y is this function times this function. If we multiply them together, 1/2 x times 2/9 y, we do indeed get 1/9 y, which was the original density function. Since we have that product, x and y are independent by definition. Now I want us to take a little bit of a note here. This had a specific kind of look to it. The density f of xy was a product. It was a product. G of x times h of y, right? If I go back up here, right, I have a product. I have a product of x and a product of y, and then this 1/9 kind of hanging out there, which you don't necessarily know where to put. And so it is essential, right? Obviously, if the density to be independent, if the density must be the product, the joint density must be the product of the marginal densities, it is essential that f, the joint density, factor into functions of x and y if x and y are to be independent. But this might happen. This might happen anyway, right? It is a necessary but not sufficient condition. This might happen anyway and yet not guarantee independence. This might happen in a dependent case as well. So it must be the case for x and y to be independent, but it's not enough. It's not enough to guarantee it. So what is enough to guarantee that x and y are independent? Well, the definition, obviously, but more than that, there's this theorem. There's this little theorem which says let x and y have joint density function f of xy that is positive on, and if I am very careful, if I specify that the support is a rectangle, and so we've seen that in our double integration, rectangles are the easy case, right? The case where you can interchange the integrals without much of a thought. You can just do anything in any order you want to. Rectangles are the lovely, easy case. So if the joint density is positive on a rectangle and 0 elsewhere, so if the support of x and y is a rectangle, then x and y are independent. If and only if, which means that now this is a necessary and sufficient condition, if the joint density factors, where both g and h are non-negative functions. Now we again need to be just a little bit careful about this. This doesn't necessarily imply that the factors are themselves the marginals. Because, right, when we look back up to this example, right, I could have factored this function up here in a whole host of different ways. I could have said it was 1/9 x times y. Well, that's one factoring. I could have said it was 1/3 x times 1/3 y. That's another factoring. Neither of these give me the marginals. The correct factoring happened to be 1/2 x and 2/9 y, which is perhaps a non-intuitive factoring. So you need to be careful applying this theorem. Just because it factors over a rectangle doesn't mean that the factors are actually the marginals, right? You have to use a little bit more care to make sure, right? The marginals will be factors, but that doesn't mean that all factoring will necessarily give you the marginals. Let us do one more example here. So this one is a little bit of a word problem. Let's imagine that we have minor damages that are due to earthquakes are uniformly distributed between $1,000 and $5,000. Minor damages due to hurricanes are independent of the earthquake damages and are uniformly distributed, this time between $1,000 and $4,000. One poor house suffers one damage of each type. We want to find the probability that the total damage is less than $7,000. So what are we going to do here? We are given this information. We are given that the two kinds of damages are independent. We're not given a joint density, but we are given information about each of them. Right? The first damage is uniform over 1/5, and the second is also uniform over 1/4. That knowledge put together with the knowledge that they are independent is all that we need to find the joint density function and therefore calculate probabilities. So how are we going to go? We're going to proceed by defining some variables. So let's let x be the damages due to earthquake. So the first thing that we were told, x is uniform on 1/5, which means that the density of x is 1/4, right? 1 over b minus a, where this is the a and this is the b. So the density of x is 1/4, and you'll notice that notation, which you might have picked up on already or you might not, right? When I said when we have two different variables hanging around, we use this notation for their separate densities. That also matches the marginal notation. So let's let y be the damages due to the hurricane. So that's the other kind of damages above we were told that y is uniform on 1, 4. So the density function of y is 1/3. Since x and y are independent, right? That's what we were told up here. They are independent. We can find their joint density. We can find their joint density because if we know they are independent, then we know the correct factors, and we can take those marginals and multiply them. And so we get that the joint density is 1/12 on the rectangle, 1, 5 cross 1, 4, and 0 otherwise. So when you are told that variables are independent, you have options open to you. You can work with them, and in particular, you can multiply their marginal densities to get the joint density. So that is the first step. Now we want to know what is the probability that the total damage is less than $7,000. So if X is the damage with respect to earthquakes and Y is the damage from hurricanes, then we want to know what is the probability that X plus Y is less than 7, which, if we do a little rearranging, is the probability that Y is less than minus X plus 7. So let us go and draw. Let us go and draw our situation here. We have this rectangle 1, 5, 1, 5 cross 1, 4. So 1 to 5 in the X, 1 to 4 in the Y. There is the rectangle that is our support. We want the probability that Y is less than minus X plus 7. Y is equal to minus X plus 7 is that line there, right, with the points on the boundary of the region that I have drawn in here. We want Y to be less than that value, which means that we want the shaded region here in gray. We want the integral of the density function over that region. And we could split this region up into different parts and integrate it, but we've seen something like this before. It is much easier to use the complement rule, and find the probability on the smaller region here that I'm now shading in green, and find that probability and do 1 minus it, right? Because we know the probability on the entire region has to give 1. So if we subtract, that is 1 minus the probability that Y is greater than minus X plus 7. So we could integrate, absolutely we could integrate. We could say that this is, well, 1 minus, this region goes from 3 to 5 in the X, from 3 to 5. And then a single Y value goes from, right, a single Y value goes from minus X plus 7 to 4, and integrate that of the density function dx dy. And absolutely we could do that. But a much simpler way of proceeding is to recognize that this is just a constant. And the same way that for a single variable, if you have a constant, you have a uniform distribution. This is called a joint uniform distribution. And in particular, when we do this integral, right, when you do this integral, that is the integral of a constant. And so you have a flat, right? So if we draw this rectangle, our rectangle is here. If we are integrating our surface above that, our surface is 1/12. Our surface is flat, right? It would be z is equal to 1/12. And so the integral would be the volume. And if we are looking for one part versus the other, the volume is going to be just the ratio. It's going to be the ratio of total areas, and that is only true because our density is a constant. And so you can do this integral and calculate it out by hand if you wish, but in this case it is so much easier to do the area of the triangle in green divided by the total area of the rectangle. The total area of the rectangle, you're going to notice, is 12, which is exactly this 1/12 coming into play. The area of the triangle above is 1/2 base times height. To save myself the integration, I have done this geometrically, and I get 1 minus 1/6 or 5/6. The last thing that we need to do then is just to generalize this. We've been working with two variables. Well, what if we have more than two? What if we have n random variables, x1 through xn? When are they independent? Well, they are independent when every single subset, so every pair, every triple, every quadruple, and so on, the joint mass or density function is equal to the product of the marginals, right? So if there's two, that was the definition for two. For every subset of a group of n variables, the marginals have to give you the joints for every pair, triple, and quadruple, and that sort of thing. So that is quite a strong condition for absolutely every single subset. So the independence, the mutual independence of the subset is quite a powerful thing.